So just to wrap things up with these computations, show in a bar graph here the RMSE values for different predictors, some of which we've looked at and some of which we haven't. So we start on the left-hand side with the simple average, which had RMSEs that were above 1 in both cases for both the training data in the blue and the test data in the red. And then when we applied the baseline predictor, we saw the RMSE drop down quite significantly for both the training and test data sets. And when we used our neighborhood predictor with one neighbor, this one denotes one neighbor, we saw it drop down again, not as significantly as it did from just with the baseline case relative to the simple average, but it still drops somewhat. And in fact, this shows the results if we had used two neighbors, the two nearest neighbors. We didn't go into the mathematical details to how you would formulate that, but you can see that it does reduce the RMSE on the training data slightly, but the RMSE on the test data actually jumps up. And again, you cannot always expect the RMSE to go down, but just on average, we would expect it to. But this data set was designed in such a way that it did not actually go down. And we spoke again about how the baseline that we used with the bias values that we computed were not the optimal values, and we said that we'd have to solve an optimization problem to actually get those optimal values to reduce the RMSE as much as possible. And this is the result if we had actually solved the optimization problem. And you see that there is improvement relative to the original baseline in both cases. So there is some more improvement we could have squeezed out of the baseline if we had optimized it. And then if we apply the neighborhood predictor there, it will drop for one neighbor, but it will drop even more in the case of two neighbors. So in the case that we did not optimize the baseline, it's interesting that the neighborhood for two neighbors does not improve the RMSE, actually decreases it. But in the optimized case, when we use two neighbors, it actually does improve it. And this is the lowest RMSE in the graph here. We get down to about 0.23 on the training data and 0.5 on the test data. Overall, though, there's no way to make a predictor perfect, because if we made it perfect, then we would be completely overfitting the data to fit exactly what we needed just for that specific case. And that's obviously not what Netflix wanted. That's not a good predictor. A good predictor has to work well in a wide variety of cases. So what we've illustrated here are some of the basic ideas. First, we talked about the baseline predictor, and then we talked a little bit about the neighborhood predictor, where we took collaborative filtering into account. With the neighborhood predictor, we actually looked across rows or across columns to extract some similarity values. And in order to get the improvements that the Belcour's Pragmatic Chaos or the other teams would have had to have done to squeeze out that improvement in RMSE on the Netflix prize, we would have to blend thousands of ingredient algorithms together really to explain that, and it's just way beyond our scope here, especially in terms of the mathematical depth. But this illustrates the basic idea, and you should now have a basic idea of how Netflix recommends movies.